Yeah, let's get started at today's session. Today I'm going to cover the Unit 5 mostly. And, we start at 6 mostly, and then let's see how fast we can finish all this. So today we are going to talk about the three things. The Integrated Genome Viewer, IGV. How many of you have experience of using IGV? Please raise your hand. 2, 3 people. Yeah. All right. So you today we will download IGV and install to your own computer and try to use it. It's not that hard. So major difference. Do you remember you guys already used the genome browser from NCBI, NIH? For that, you have to be connected to the internet all the time, basically. But if you install this genome browser locally to your own computer, like IGV, you don't have to get connected to the internet. You can use that. So it's the genome browser, and the another very helpful genomic resource. There are actually 3 major genomic resources that we are going to teach in this class. The first one was NIH NCBI. The second one was the last week, which is Ensemble, from the European the resource. And today is the last one, which is UCSC, University of California, Santa Cruz. Yeah, so we will explore. We will explore the UCSC resource today, and also we will explore the Galaxy too. This Galaxy is not the Samsung Galaxy; it's a different Galaxy. Yeah. So, how many of you ever have experience of using this Galaxy in the cloud for genomics? Please raise your hand. 3 people. Yeah. Don't worry. So we will get to use, and yeah. So today's main goal are, let's try to use the download and use the local genome browser, what we call IGV as a vector, and then let's use the UCSC resource, and let's try the Galaxy. So those are the 3 main topics. In genomics, there are some major institutes. NIH is one of the main institute that play an important role, and European Bioinformatics is also another big institute, and also the University of Washington or University of California, Santa Cruz, UCSC. And in addition to that, there is a Broad Institute in Boston. Is there anyone who know about the Broad Institute? Yeah. Have you been to the Broad Institute? No? Broad Institute is located in Boston, Massachusetts, which is about 8 hours from here, or 7 hours from here. And the Harvard University and MIT, they jointly founded this institute. And Broad Institute is specialized in genomics. So a lot of researches were done, and it's being done. And since a lot of genome researches are done, they even made genome browser for the research, and they provide this for free. Because can you turn off the audio? Okay, great. The main reason is yeah, they are mostly funded by public grant. So anyway, they made a genome browser for the genomics research, and they publish it. And so we want to use that. Now, IGV stands for Integrated Genome Viewer. It's basically one genome browser. With since you are going to install locally, you don't have to get connected once you download and install this. But this requires a Java. So, for example, this is one of the first things that I want to do with together. So we will spend some time, and I want to make sure that everybody can install and actually run the IGV and actually get into this the IGV page. Please download and install IGV locally into your laptop or desktop. And since my computer is the MacBook, and what I downloaded was this one. I downloaded this version, and I installed that. So yeah, let me give the 1 or 2 minutes. Can you guys install and then let me know any technical trouble? So upon installation, and then if you run it, I want you guys see something like this. Let me show that. IGV version 2.2-16.2, and this is the genome browser, and I want you to select human HG38, and this is the screen that I want you to do. Oh no, sorry, why not? Sorry for that. Let me do it again. Okay, so IGV version. Oh yeah, let's see. Yep. So this is IGV genome browser site, and please choose the human HG38, human genome version 38. The reason why I want to make sure that you can install and see this is some homework may require you to do the screenshot of this IGV, and I want to address any technical problem right now. So how many of you successfully installed this one? Please raise your hand. How many of you have a trouble? Some trouble? No one? Great. Okay. This is the genome browser. Genome browser allow you to browse the standard genome, right? How many base pairs do we have for chromosome 1, approximately? Pardon? About 250 million. So just imagine this distance. When you add up all the haploid the bases, it ending up with the about 3 billion, right? But chromosome 1, which is the longest one, is about 250 million. So what is the position about in the middle? About 125 million, right? So I wanted you to type like this. You want to go to some place, and let me put it in the chat. I want to go to the middle position, which is chromosome 1. The middle position is 125 millionth position, right? So what I want to type is chromosome 1 colon Just one moment. I'm going to send in a chat. So I just sent it a chat, and I'm going to paste it here. And do you see that I pasted in the search box and click go? Did you go to that place? One thing that I wanna address is instead of a chromosome 1, CHR1, can you drop the CHR and can you try without the CHR? Let me delete. What happens? CHR and press enter key. And press enter key. And then somehow it automatically go replace with the CHR. So standard notation for chromosome 1 is CHR. So, and then followed by number and colon and then position, beginning position of that, and then ending position of the interval. So that's where you are looking at. So even though I asked, show me the position of a chromosome 1, 2.5 millionth position, right? That's what I typed. But what they interpreted was, okay, that is a 1 base pair. Let me add 20 base pairs in front, and then another 20 base pairs to the end. So they made about 40 base pair long interval. Do you see that? Okay. And is there anyone who happen to know, translate that into the bioinformatics language? Padding plus minus 20 bases. So that's the meaning of a padding in bioinformatics. So to the 5' end we added a 20 bases, and then to the 3' end region we added another 20 bases. So basically we added a plus minus 20 bases padded. That's what we say here, right? And then yeah. So do you have any question here? The coordinate, right? Format is CHR number, colon, beginning position, dash, ending position. Pardon? Colon. It should be a exact colon. It cannot be a semicolon. It should be the colon. So this is a very strict, like what do you say, format. Yeah, if you want to be creative, try it, but most likely it won't work. Okay. Now, and this region is the in which gene? How can you find out gene name in this region? If you carefully see the down, do you see that the FLCH2 name here, down there? Here. All right. And so the bottom is the reference genome sequence, right? Why there are so much blank space in the middle? What's the use for that area? The central region, which seems to be very important, right? But it's basically blank. You are going to, do you remember, did you learn about the bed file last week? And did you, do you remember the week file? We made and prepared that kind of things, right? You can upload that by using the file load from file command. So once you prepare that some genome interval file, like a bed file, you can upload it and you can visualize the interval here. So those goes into the middle. So you can look at your own data that you prepared with reference genome, right? That's why it's in the middle. Middle region is the blank. And I show you this feature. Do you see that the plus and minus button here? Zoom in and zoom out button. Can you press the minus button? When you press up to here, just one minus, yeah, it zoom out slightly. And if you carefully see the basis, T is denoted as a red color, C is denoted as the blue, G is the yellow, and A is the green, right? Let me zoom out one more time. Do you see that the ACGT is gone, but it's color coded still? So by looking at the color, you can still say, okay, which base it is. And yeah, honestly, I don't even remember which color they use. So whenever I need to see the color, I just go here and then I magnify and check, okay, C is the blue color, something like that. Then actually go back. And if I zoom out further one more time, yeah, color becomes narrower. And if I do one more time, now some thick block is shown up, and there is a thin line with a gene name. What is this thick line? Thick blocks. What does it mean? It means exonic region, and this thin line means intronic region. And then, do you see the arrow, direction of the arrow? That means gene is in the forward direction. Okay. If you continue to zoom out, when you zoom out this much, now you see some other gene shown up. And this PLCH2 gene is in the forward direction, along the forward direction. But another gene, PANK4, PANK4, is the opposite direction, right? Now, shall we explore the PANK4 gene? And let me just show you one tip that I'm using. You know, this is in the bottom, right? And the position is up. So it's not really convenient. So can you carefully bring your mouse here in this borderline? And then when you bring that to the borderline, does it change the icon as an up and down arrow? Do you see that? Now click and drag it, hold it, and then move it to the up. Why? Because by doing so, it should move up. Why it doesn't move up for me? I don't know. Pardon? Which lower line? Which one? This one? Yeah. Yep, thank you. Yep, this one. Yep. Now, can you highlight this gene? And can you double click or right click? In my MacBook, I usually click with the 2 fingers. to see the menu like this? Did you do that? The right click or click with the two fingers? And do you see a lot of menus here? And the default is collapsed. Collapsing what? To answer that, why don't we try to choose the expanded? When you look at the expanded, you will understand the meaning of a collapse. So can you guys choose the expanded? Okay. Is there anyone who's get lost what I'm doing? So simply, I just ask you to right click and then after this gene, and then choose the expanded. And you just expanded the gene annotation information. Now you can check out isoforms of the gene. Previously, you had the representative view, but now you have all the individual isoforms expanded way. Do you see that? And now I'm going to focus on not this gene. I want to focus on the other gene. Gene name is a PANK4. Even though you can type the coordinate, I don't know the coordinate. So what I'm going to do is I'm going to click and move it to the center. Can you move this PANK4 in the middle? Did you move this PANK4 in the middle? And then, is there anyone who can explain this meaning? This thing. Big block, big block, big block, followed by middle-sized block. Not really the line, but middle-sized. What is that final thing? You said this, what is it? Big block is the exon, right? Then what is the meaning of this intermediate size? Not so big, but not the thin line. What is that? Yeah. In this case, is it 5' or 3'? 3' UTR, untranslated region. Okay. Right. So now, shall we magnify and shall we magnify? This is a 2.5 million position out of 250 million base pair long chromosome 1. So which should be really upstream, 5' end of it. So do you see that the top view? This is really in the 5' end region because it's a 2.5 million position out of 250 million position. So there are 99% waiting behind it, right? Now, can you guys magnify to see some exonic region? Just choose any exonic region of the PANK4 gene. And did you magnify any of this? Okay. Now, yeah, can you look at the A? Just browse and then find the A. What is this A means here in the middle? What is that A? Pardon? A is the amino acid. It's not the A in the DNA. It's A in the amino acid, alanine. Is there anyone who can tell me the codon, DNA codon for amino acid A. Can you, is there anyone who can actually type it in the codon table, like for decoding amino acid A? There should be multiple. Yeah, can you actually type it in the chat? And all of them, not just the one, but codon GGC and TGC code for the amino acid A, right? Okay. Now let me. Are you sure the TGC really codes for the amino acid A? Let's look up the codon table together. Codon table, amino acid. Yep. Which one is alanine? Alanine is, where is it? Oh, here. GCU, GCC, GCA, GCG. So those are the 4 codon table right here. And for the U, just use the T. So if I type here, if I just wrote it right here, GCT, and the GCC, and GCA, and GCG. These 4 can code for alanine. Right? Now it's time to check the DNA sequence from IGV browser. And for this particular IGV browser, it's a TGC. You know, I'm doing this on purpose. TGC is not in this codon table, right? It's not A. It's not coding for A, right? What's going on? Because this gene is located in not the 4 strand, but backward strand. You have to do reverse complementary sequencing. In IGV, is there any such a button? Do you see the this button here? That button? Yeah, this button. Since this gene is located the other way, 3' to 5', to see the real sequence, you have to do this. And then one more thing, you have to read from the other way. Gene is located this way, right? So now the first base that you have to read is, you are tempted to read from here, 5' to a 3' direction, but no, you shouldn't. You should read from 3' to 5' direction. And do you see that GCA codon, which actually matches here? Yeah, I actually chose the very complicated example so that you can familiarize with using the IGV. So this example shows you that by using Genome browser, yes, you can check DNA sequences, but you have to be careful whether gene is in the 4th strand or backward strand. If it's a backward strand, you have to reverse it by pressing this arrow icon, and that's not enough. You have to read from the other way. When you do that, that should match the codon table. Does it make sense? Pardon?
When you press that arrow, does it convert to complementary?
Yeah, okay, the question is, when I do that, what's happening? Do you see that G? What is the complementary base of the G? It's a C, right? So it's going to be C. What is the complementary base of T? It is going to be A. So it's just a complementary sequence, but you have to read from the other direction. That's why after you make a complementary, you are not reading this direction, you are reading the opposite direction, GCA. So directionality, you have to take care of it. But the complementary base is automatically done when you press the arrow. So what we usually say is reverse complementary sequence, right? When you use the genome browser, complementary sequence can be obtained by arrow key, but reversing, you have to do it yourself. Does it make sense? Right. You just consider U as a key. Yep. So I hope that this address all the concerns about how to utilize the genome browser, especially the DNA sequence and codon table, gene in the forward direction and gene in the reverse direction. Okay. Okay. Now, is there anyone who can explain this picture in the top? This is chromosomal view, right? We have a P arm and Q arm. Which one is a P arm? The short one, usually in the 5' end. Yeah, the one in the 5' end. Q arm is a usually longer one, which is in the 3' end. So that is the left part is the P arm, and then the right part is the Q arm. And we are looking at really beginning part of the P arm. And then do you see that everything starts the P here in this section? And if you go to the right side, everything starts with a Q. That's our P and Q arm. And you have a band. When you dye it, yeah, we have the dyeing band the designation. So if you want to know some more detail on that, you can just click to see it. Right? And okay, let me just go back to the and I just want to show you two more things. Let me move it back to the like a collapsed view, or you can try the squished view. Squished view is it's like a full view, but you want to minimize the height. That's what the squished mean. But let me do the collapsed view. And this is a very minor thing, but it's handy to know. I want to customize my annotation. This is my reference sequence. So I want to just call ref. That's what I want to call this. Or so right. And then the rename track. Do you see that the rename track? And then let me just rename it as I wish. Reference ref. I just rename it reference, right? And I usually want to change the font size. Change the font size. Now the default is a 10, which is way too small. I probably put the 30 or 20 and double this, right? And then one more thing I want to do is I want to change the track height. Change track height now it's 40, but let me double this 80. Then it becomes like somewhat bigger. So that kind of a customization is I'm often doing when I use IGV. And you can do the same thing for another track that you are going to add here. If you prepare have you guys ever seen the reference genome? No? Yes? Reference genome is nothing more than simple FASTA formatted file. So simply, FASTA file is to denote the sequence. We usually use the FASTA file, and greater than sign followed by the you can just say CHR, let's just say CHR 30, chromosome 30. Now ACGT sequence. So that's basically the reference genome. That's the reference sequence in the FASTA format. If you prepare that, if you have that FASTA file, you can use the genome load genome from file. You can upload a custom genome here. Okay. But since HG38 is pretty standard, you don't have to because it's there by default. And then you can load the many files in the middle from the server directly. You don't have to download it to your own computer and load it, even though that's allowed. So you can either download it, upload it manually, or you can directly upload the data set. Yep. Any question on the IGV? Yeah. How do you load what? Oh, new track. Yeah. Why don't we actually do that exercise? You need your custom file. So since you don't have a custom file, let's make it one. This is the interval, right? So shall we make this interval as a bed file? Interval is mostly well visualized using the bed file. So what is the best way? I usually use the command line, but let's try to use the text edit, whether it works or not. If it doesn't work, I will use the command line. But let's see. Okay. Text edit. And then I want to make a new document. And then zoom in. Okay. I want to copy this. This is some random interval. But this is not the bed file format. So I have to follow the bed file format. Do you guys remember the bed file format that we used? Chromosome 1, and then press tab key. Tab, I press the tab key, not the space bar. And there should be no colon, right? I delete the colon. And there should be no comma. It's better not to have this kind of thing, weird thing. And then at the end of the first interval, starting interval, I press the tab key again. And here, so I prepared this way. CHR1 followed by one tab key, not the two, just one tab. And then starting position of the interval and the tab key, ending position and ending. So I just made a one-liner. Let me save it, file, save. Let me save it to the desktop. Test1.bed. And the problem is that this rich text document is not working properly. I should have used the regular text version. So why don't I actually try? Let me just copy this and let's use the Microsoft Word. Okay. So I just did that same thing in the Microsoft Word. I want to make sure that it's separated by tab and it's separated by tab. And I want to save it as a text file. File, save as. Desktop, not as a Word document, test1.bed file, and plain text format. So I chose the plain text file, and then my file name is a test1.bed. Let's try whether it works. Okay. Let's use the default one. Okay, let's try it. Now I have a test1.bed file, and let's try to upload it. Load file, load from file, and then desktop list test1.bed file. Yep, I just made this interval, upload it properly, and do you see that when I zoom out, this is the beginning of the interval, and this is the ending of the interval. And let me do the same thing. Rename that, not the rename, change the track height to 80 to make it bigger. And then font size, yeah, let me double this. Yep. So this is how you upload the custom thread. You make a file, either bed file, weak file, or FASTA file, FASTA file. And then once you have it in the plain text format, click file and load from file. So let me just show the Word file. It will work, yeah. Variation viewer works, and actually it will work anywhere. If you save it in the plain, for those who prefer to use the command line, CD desktop, you can use a VI or nano, but let's use a nano. Test2.bed file, paste it, and then Control X and save it, and press Enter key to save it. So now I have a test2.bed file. If I cat the test2.bed, it shows the content like that. And now I'm going to try to do upload the test2.bed, which should be the same. File, load from file, and then test2.bed file, and then load it. So now I have the test.bed file. Yeah. Tracks are blank. Did you go to the right coordinate? No, no. This is the like a location, right? Do you remember colon, this, and minus this? So, okay, can you share your screen? Yeah, please share your screen if it's okay. Yeah, we can troubleshoot together. All right, it's blank. So I want you to go to the place where that interval is defined. So can you show me the Microsoft Words that you did? What's the Microsoft Word? Yeah, can you actually copy this? Can you show me the move it? Go to the chromosome 1. Can you use the right arrow key? Yeah, good. It's a tab. That's good. And then is there another tab or right? Okay, can you copy this region? Okay, and then paste that into the IGV. But you have to use that format, colon, and then dash, yeah. And then can you do the minus? Hit the minus for the zoom out. Yeah, that's the interval.
When I'm using bedfile,
yeah,
it already has the interval set. Is it not going to automatically set what I'm looking
at? Yeah.
Yeah,
you have to go manually. Yeah. Yep. So any questions so far? The IGV? So basically, IGV is the locally installable genome browser. You can explore genome with your data. And then how can you upload your data? Yeah, just get the batch file or weak file or FASTA file. And once you have it, then just use file upload, load from file option. Then you can have it. So did it work for you guys or not? It worked? Okay. This file, which file? Batch file, weak file, those are your own file that you generated, right? No, reference genome is a FASTA file. Only FASTA. Batch file is for interval. Weak file is trace showing that trace. This is a FASTA file. FASTA. For sequence. So this is the FASTA file format. FASTA file is to denote the sequence. We use the FASTA format for showing the reference sequence. Yeah, let's try then. All right. Yeah, let's try a new document. Greater than sign. And yeah, let's just do the chromosome 30 of some new organism, not the human. And ACGT, 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 ACGT. I just made it up. Reference genome is like that. File, save as chromosome 30.FASTA, and then format should be plain text. Okay, let's do that. Okay, I made a chromosome 30.FASTA file. And file, load from file, chromosome 30.FASTA, and hit the enter key. Oh, yeah. I have to remove the .txt. Somehow that .txt is automatically added, which is not desirable. So I edit that file, load from file, chromosome 30, and open. Check. All right, let's try. Okay. Let's try to use the FA for the extension. Still not working. Just one moment. Oh, the file is not there. File is not properly created. So when I do the cat, why don't I just use the nano chromosome 31.FASTA? Control X, Y, and hit the enter key. Try. Oh, this is not the file. This is a genome, right? Genomes and load genome from file. Yep. So I made it chromosome 31, and like that. It's the my let me just try to reproduce what we have done. Yep. Let's save it. Let me try to load the genome. FASTA file is a genome file, so I have to use that. Yep, it's working. Pardon? Chromosome 30 and ACGT sequence. Yeah. So I made the artificial, like a chromosome or artificial organism, and which is a reference genome for artificial organism. I save it as the FASTA format or FASTA format. And when I upload, it's not the file, it's a genome. So genome, load the genome from file. Then you can upload your custom genome file in this way to the IGV. But let me go back to the human HG38. Yeah. If you sequence a new organism, you can create the new reference genome. You can upload it here, and then with your own data. And by sequencing another organism, you can compare here. So basically, the IGV is this kind of a tool. You can actually compare any sequence-related information. You can upload your own genome. You can upload the any like a interval or any Uyghur file, and you can compare, see that in the context of the reference genome. Okay. Yeah. Before we take a break, I want you guys try to answer this. It's a human HG38 reference genome, human genome version 38. Which base is it for chromosome 17, 43rd million, 57,063rd base pair in the forward direction, not the reverse direction, in the forward direction? Which base should it be? what is the base, A or C or G or T, that correspond to this position? Is it A, or is it C, or is it G, or is it T? Pardon? And how many of you think it's a C? So, okay, one vote here. Any other opinion or anything? It's a forward direction. I'm asking the DNA base in the forward direction at that position. G. 3 people says G. Right? Let's do it together. Let me copy this. And then making sure that HD38, right? And then paste it here. And making sure that 7063rd base, that's what I want to see. And click go. And even though when I do that, it's in the middle, right? I want to magnify further. And then making sure that this is the forward direction, right? Left to right direction. And this G is the, this C is the 60th, 61st, 62nd, 63rd. So 63rd base is G in the forward direction. In the reverse direction, it is 1, 2, 3, C. So if gene is located in the backward, you have to press this to see that. If it's a forward direction, you have to look at this in this way. Now I have one question. The one question is, hey, what is the base for this position? So I didn't even specify forward direction or backward direction. I'm just asking, what is the DNA base for that position? Then scenario 1, you just tell it's G because it's a forward direction. Or you ask me, are you asking for the forward direction or reverse direction? Then answer. What is the constant in the bioinformatics? So if somebody asks, what is the DNA base for that position?
It should be forward.
It should be forward. Forward is assumed. So no one usually asks, is it forward or reverse direction? Everybody assumes that if gene is in the reverse direction, make it forward direction by the complement, and then answer it in the forward direction. Even though the gene this gene belongs to the BRCA1. BRCA1 is the reverse direction. But when you actually say, and what is this DNA base, we usually assume the forward direction and tell you, okay, this is G in the forward direction. So don't confuse that. If you want 100% sure gene is located in the reverse direction, and then according to the reference genome, if you make it complement, the DNA base in the reverse direction is C. You can say that, but usually without any assumption, if I just say, hey, what is the DNA base for that position? Just assume I'm asking you the DNA base in the forward direction and just answer it. Because these kind of things are assumed in many databases without clearly written. So you might get confused, but that's the reality. Right? Any questions before we take a 10-minute break? Right, let's take a 10-minute break. Yeah, if you have any question, you can ask me. Even the online people too. Pardon? Oh, PPT. Yes. Yeah, we will resume at the 7:15 p.m. Okay. Yeah.
So this is a reverse trend, right?
Yeah, that's a reverse.
So if we do this,
Yeah.
it still shows this direction.
Pardon?
This is in forward base.
Yeah.
So if it's this, then it's forward base. And if it's this, this is reverse base.
That's correct. But the breakout one is the distraction, right?
Yeah.
So the S should be distraction, right? And then S should be read from distraction. TCC. Not like a CC.
Yeah.
Yeah.
Okay. So and if it's in the forward direction, then so this is no. If it is like this, then S is we read it this way.
Yeah, GGA. But that's wrong. Yeah.
And so if you ask what base is for reference, that number,
Yeah.
so we will say G in forward direction.
That's right.
So G is at 63, right?
Yeah.
How many? So 15 numbers at this. No, 60 is there.
That's a 60. Yeah.
62. This is 60.
Yeah.
How?
The line.
Okay.
Line in the middle. Yeah. Yeah.
When I'm uploading the file, do we upload from G?
Faster file is uploading from Genome, but the bad file, weak file uploaded from here.
Okay, so the
Not the bad.fai, but
no, it's this one. The bed file is not opening for some reason. I did it with so
yes, I did that. Okay, that's good. Oh, it's in the top directory, not the desktop directory.
no, I have it here.
Where?
Desktop is here. So I put it in a download. And I exit this to this here.
Oh, you are in the downloads. Okay,
Yeah, okay, I'll just do it again.
right. You have it in the download section.
Yeah. So here this I go here
Yeah.
and go to
That's IGV.
yeah. So when I do this,
Yeah.
it's not
And then, can you show me the file content again?
on this one.
Yeah.
It's here.
Yeah. Can you copy this? You have to go this place
Okay.
in the IGV. Can you paste it?
Yes.
This is a chromosome 17. You have to go to chromosome 1, but in the right format. Delete that, yeah, colon, and then minus. Sorry, yeah. Delete that space, minus, yeah, enter, or go. That's this is the interval. Oh, no, sorry. I want to have a collapsed view.
Okay.
And here is the test of that.
So,
right? So if you do the minus, yeah, this is the interval.
Okay. Thank you.
Yep.
Okay, so I got the last thing you asked us. My question is, for this one, the first one that you asked us, I think we get to upload the file. I just have a few questions. So it seems like my tabs are much more longer than this one, the test bed. When I put it in Word, my tabs are like much more like longer, and like when I uploaded it, it was like a blank screen.
Oh no, it's right. It's okay. Longer is okay, but as long as you have only one tab.
Yeah, like it's just so long.
Yeah, only one.
Yours.
That's okay, no problem.
And then when pretend this was chromosome 1.
Yeah, but did you save it to the text file format?
Yeah, I'm gonna do it now. Plain text,
plain text.
and check out fast. Right, that's it.
Not bad.
No.
The bad format. BED.
Okay.
Yep, but save it.
Okay.
Yeah.
And when I go to IGF, I go to genome. Look.
Bad file is not the genome file. Bad file is just the regular file.
Oh no, what was the thing?
Best file is the genome file.
Yeah, but you did something with
Yeah.
that. What do we do?
Yeah, in this case, you made create the bed file.
Mm-hmm.
Bed file is not the genome file.
Yeah.
Bed file, you have to click the file.
Okay, okay.
File, load from file,
Okay, file.
and then choose that.
This one, yeah. Okay.
Okay. Yeah. And then now, this is a chromosome 17, not
Chromosome
chromosome 1.
one,
So
okay.
can you actually go to copy that location?
From the Word?
Yeah, from the Word.
Sorry, I have like so many tabs open. This one?
Yeah.
Okay.
Paste it here,
And then do the
right format,
yeah, right.
and then delete and dash. Yeah, go.
Yeah, go. Oh,
Oh, yeah, you have to
do it
click
again.
the go, yeah. But then let's delete that and then do it again.
Okay.
Column, yeah.
And hit go.
Yeah.
Okay, thank you.
Right there, yeah.
Thank you.
Yep.
So a question. So I was trying to do the discussion as well.
Yeah.
And the IGV basics, is that what we just did?
Yeah.
So you just want me to try the exact same thing in 1819?
Basically, yeah, anything fine. Yeah.
Okay.
Just try any basic operations.
Okay. Sounds good. Thank you.
All right, let's get started again. Hello everyone, let's get restarted. Then let me do the some. I like to ask the questions to you guys as you have noticed. Can you raise your hand if you belong to group one? Group one. Here. Let me share that. Here, the group one, group two, group three, and group four. Yep. So, do you guys know your group? Yeah. Raise your hand for the group one, please. Okay. Group two, group three, group four. Okay, good. Yeah, I would like to do some interesting project right now. So after I introduce some like UCSC Genome Project and UCSC, then I will let you guys collaborate without in your own seat and using this MS Teams and answer these questions in a collaborative way. And then when I ask hey, it's a group one's turn, can you tell me how many base pairs for the BRCA1? Yeah, and if I ask, can you share your screen, one of you, and actually, can you show me how you get it? Yeah, something like that. So we will do some good part in this class. So let's be open-minded and let's try. But yeah, let's get started about this UCSC. So this is the third, I told you the three major genomic resources. NIH is the NCBI in NIH, Ensemble, the European Bioinformatics, and the third one is the UCSC. I'm very impressed about the UCSC because UCSC is just one university, but and it's not really that super big university or like that. But somehow in genomics, we cannot exclude UCSC. It's so important. So that's why when I first asked you, hey, can you guys get the sequence of BRCA1? And in the beginning of the this in-person lecture, probably unit 1 or 2, we use the UCSC table browser. That's what we use without really introducing. Today is actually the day for like a formal introduction of the UCSC research. So UCSC provides multiple resources. One of the resources that you guys already tried was table browser to pull down the sequence of a BRCA1. That's one resource. Another resource that they provide is Genome browser. But let's do let's think about it. NIH provide NCBI provide the NCBI Genome browser, basically, right? Ensemble provide the Ensemble Genome browser, and UCSC provide the UCSC Genome browser, naturally, right? And some Genome browser has some pro and some con, so I cannot say which one is the best. It depends on your purpose. And now, do you remember when I asked you, is it possible to pull down the BRCA1 sequence? You used the UCSC resource, table browser resource, in the first session. But did you notice that you can do the same thing in Ensemble, or you can do the same thing in the NCBI, right? And likewise, do you guys remember the BioMart? Is there something similar here? Yeah. So basically, these three resources, NCBI, Ensemble, and then UCSC, provide a similar kind of the information. Are these information matched exactly or not?
No.
Unfortunately, no. Yeah, that's a pretty short and strong and correct answer. That's good. Then what should I use then? I'm asking, hey, I want to get the BRCA1 sequence. So then, and I already told you that the sequence of a BRCA1 in the UCSC is not the same as exactly the same as the other two. Then what should I do? When you actually write a paper or manuscript, we are saying that, okay, here is the BRCA1 sequence according to UCSC version something. So as far as you specify that level, yeah, then for BRCA1 sequence in Ensemble which version. We use the BioMart to put it with that command. So when you actually provide that much detail, then now we can verify whether you did it correctly or not, and then now we can reproduce it. This resource, by now it's not that really new because you know what to expect. Genome browser, and then pull down the lots of sequences and some or other relevant information, and biomark like a function, but not exactly the same, but using the table browser. So basically, we are going to repeat, but you want to get familiarized yourself so that you can actually pull down the relevant information using the UCSC Genome Project. So yeah, I was pretty surprised that they were actually, UCSC happened to be the leader in this field for a long time. So I was quite impressed of what they were doing. And I just want to add one more thing. Which reference genome do you guys use mostly? HG38, right? And let me just tell you the story. Do you know what is the HG stand for? Human Genome Version 38, right? So what is the previous version?
19.
Why not the HG37? What about, why not the HG36? Why the HG19 and then simply jump into the HG38?
They perhaps use 19 individuals.
Pardon?
They perhaps use 19 individuals for doing the reference genome.
19 for
19
individuals?
For doing the reference genome.
Oh no, actually, they it's basically 19th version of 19th reference genome, not 19 people.
That's right.
Yeah.
You asked why 19, but not 36 or
You
35.
see, maybe there was just 19
Maybe there was
people.
19 people. That's
Yeah.
why they get
Actually, yeah, good guess, but it's not. Okay. Now I would like to explain some more some story here. Is there anyone who heard about the GRC? That stands for Genome Research Consortium. That's the main, what is that, organization that publishes reference genome. So GRC, the major institutes like the Washington University and Broad Institute and all these major players make a company there, and then they regularly publish. So GRC, H means the human. Genome Research Consortium human version. Let's start from the very beginning. What is the biggest version? What is the biggest version? 36, like that. Genome Research Consortium regularly updates, and they would like to add some more like telomere sequence or centromere sequence, and then try to do some more accurate sequencing, and then provide that. So every version improves, isn't it? And as you can see, yeah, if you look at this, yeah, it's pretty regular and like that. The UCSC always use the annotation like HP. So HP 18, HP 19. The UCSC did not have a resource to keep up with regular version. UCSC is just one university, right? So HG18 is the 18th human genome version according to UCSC, which corresponds to this 36. And HG19, 37. And everybody gets confused. Why don't we actually use the same number? So UCSC decide to skip all this and use the same number. Yeah, this is the other story behind it. But you don't have to remember. But I just tell you because I was in this genomics field. Yeah. Anyway, so now the best way to learn about the research is, I believe, that by timing. So everybody here know that which group you guys are belong to. Group 1, 2, 3, 4, right? And do you guys have access to MS Teams? So I'm going to ask these questions. And can you guys collaborate? I'm going to give the time later. Just give me 5 minutes. I just want to explain the details. Then I'm going to give you time, about 10 to 15 minutes. Then when you guys are done, I will ask the each group and then show the logic. Answer can be wrong, that's okay. But I'm more interested in your logic and how you approach that problem. That's so don't have too much pressure, even though you do not get the correct answer. Everything is in the process. I value more on the process, how you guys are doing. Right now, let me explain the process. How many of you know the 23andMe? 23andMe? And you know what the word the 23 means, right? 22 autosomes and 1 sex chromosome, right? That's a 23andMe. And it was founded by
The founder of Google's X1.
Yes, actually that was what I was trying to say. Anyway, thank you. Yeah. Anyway, 23andMe is the B2C company. B2C genetics company. You guys know what is a B2B and what B2C? B2C means business to consumer. Sometimes we classify the 23andMe as B as a baby, 2C. What is the B2C means? Direct to consumer. And since you guys are learning the genetics, I'm actually actively in the industry field. So I would like to actually explain some of complications and regulations. 23andMe, is there anyone who uses the 23andMe service? Yes. If you pay about $100, $100 to $200 range, depending on the promotion, sometimes $79 something, you get the ticket. You get the kit. Kit is going to be delivered. And in the kit, what did you do?
Like, give you a sample.
Yes. And you basically put your split there, right? And I since you actually have done the experience, do you still remember the amount that you split? No, you don't remember. Actually, it is actually split the kit. Yeah, you may think it's a little bit of amount. No, it's not. You have to split a lot. Yeah, really. Then many people, this might be the very challenging time in your life. In your life, you will never split that much within the decimal amount of time. That's what I can guarantee. Yeah, it's a relatively big.
Yeah, it took me like 2 years.
Yeah. Yeah, that's right. I'm not surprised. One of my friends who tried to do it in that spot, minimizing the variability, and he said that he after doing that he even felt pain here, and then used up all his 2 days of saliva. Right? Anyway, when you do the spitting, what's contained inside?
There's like some kind of preservative or something like that.
Yeah, there are preservatives, but what's in your saliva? What's in your saliva? Cells, right?
Yeah.
What type of a cell? Sheep cells, there could be some, but I don't expect a lot of sheep cells because you have to scrape it. Yeah, there should be some, right, but not so much. A lot of them are white blood cells. Not all of them. And if you happen to sequence it, you will surprise that you are sequencing more of your microbiome rather than yourself. A lot of the sequencing data actually goes there. You're basically wasting a lot of the sequencing information there, and also it also can potentially cause some error. Even though microbiome sequence is pretty different from the human, but still there is a possibility of a potential error. Right? Okay. Let's say that anyway, from the spit, you extract the cells, white blood cells mostly, and then from the white blood cells, you extract the DNA of yours, and then now what? Sequence? No. 23andMe are not doing the sequence. 23andMe are using SNP chip technology. Is there anyone who know the difference between SNP chip versus DNA sequences? Yeah.
SNP chip is like chip sequencing, and like how in chip seq we sequence particular proteins. And here they have like a panel of SNPs which are correlated to some diseases, and they are just extracting those SNPs and they are sequencing that. So it's not whole genome sequencing, but specific bases they are sequencing to see the variants and then predict what diseases could happen.
Good try, but actually it's not. That's why I will explain here. And use the SNP chip. And what's the name? Yes, Kaizen explained this. That's what you explained. Chip. So this chip and this chip, even though the spelling is the same, it's not the same. This is chromatin. I means immuno. T is critical. After you do that, you perform sequence. Using NGS. Let's do it. But this is simply microarray. this microarray chip has, it depends on when you ordered. If you ordered a couple of years ago versus now it has about 1.4 million spots, but a couple of years ago it has about 500,000 to the 0.7 million. So it has a multiple. At this time, it has around 1.4 million. What do I say? Yeah, let's say well. Each well can measure one variant. So variant 1, variant 2, variant 3, like that. So by detecting the color of this, you know that whether that well has a SNP or not. If you do not have the SNP, your genotype is the same as the reference. If you have the SNP, your genotype is different. What is the typical SNP ratio compared to the reference genome for a regular person? 1/1,000. So 999 are the same out of 1,000. So roughly, just roughly, if you have a 1,000 wells, one of them may be different. That's rough, like an estimate, right? So this is the SNP sheet. So 23andMe use this technology to tell you which SNP you have. Okay. Now, they actually started with ancestry. So if you use this service, you can actually say, okay, I'm a Korean, so I'm 90% of a Korean, 8% Chinese, and 1% Japanese, something like that. Or if there is a white people here, probably 70% Italian and 20% of Norwegian or something like that. I don't know, something like that. So they use this for that kind of thing. By the way, do you know how to actually get that information? How is it possible to get? You have a 70% of like Italian, something like that. Have you ever heard of PCA, principal component analysis?
Yes.
Do you happen to know 1,000 genome project? Yeah, basically 1,000 genome project is we sequence the 1,000 people. Like let's say 100 Asians, the 200 Italians. I'm just making up. So you can have that, right? So we have that 1,000 genome people's the database, and using the principal component analysis, you actually compare your genotype to that person's genotype, and just see where your genome is clustered with Korean or with the Italian. So that is basically how it's working. Anyway, so I just want to tell you about the industry too here. When we are talking about,
So according to you, how accurate is 23andMe microarray technology for diagnosing or predicting diseases?
around the 1% error rate. So if you make a 1.4 million, how many bases could be wrong? How many things can be wrong? 1% of it. And 1% of that is a lot, actually, right? So, but what about the NGS? What is the typical error rate at the end when you do all the downstream process? around 10 to the minus 5 or 10 to the minus 7. When you final like value, when you align it with the mapping and proper control, and then when you finish. But for the seed chip, you cannot get better than that. But in NGS, eventually you reach that state for the variant quality.
Then how come 23andMe has FDA approval?
Yeah, that's why I want to actually explain some detail. I want you guys actually understand and know the industry too. So when they started, they focused on the ancestry. FDA, Food and Drug Administration, said, that's all right, why not? It does not give you a harm. Okay, no problem. But they actually started to service on medical things, such as, do you have any risk for heart disease, Alzheimer's? Yeah, there are some known variants, right? If you have BRCA1, breast cancer, right? Everybody here knows that if you have a certain BRCA1 mutation, yeah, you have an increased tendency for breast cancer, like that. We know the variants. So anyway, they are testing 1.4 million cells, 1.4 million, and many of them are BRCA1, right? And they wanted to expand. So they started to service on that. And you know what happened? In 2013, about 10 years ago, FDA says provide enough evidence that your technology is good enough to claim it. And what happened was, AS.410.635.01.FA23 did not respond to that FDA letter, and then just retrieve that service from the market. That's 2013. But not now, right? And they were just concentrating on the ancestry. But did you know that medically we use the imaging technology or GWAS, genome-wide associated studies, and many studies? And think clearly that, yes, these guys are doing, why not for us? The problem is a B2C, direct to consumer, B2C. That information is, but most other cases go to the doctor. But they simply send the information directly to consumer, which can be misinterpreted, and most of the consumers don't know that kind of things. And most of the consumers doesn't even know how many hits can there be for BRCA1. Right? So FDA was concerned that kind of direct to consumer. Not the technology itself is fine as long as correctly used and interpreted, because the seed chip is medically used. But the problem is it's directing towards directly to the consumer without any doctor's information. So what they did was hey, these guys are doing BRCA1 tests. Why not for us? Let us do the BRCA1 test. And they filed that, and then they got the approval in 2018. So in 2018, 23andMe got the approval on doing the BRCA1 test so that they can tell about the breast cancer. So after that, 2018, you get the BRCA1 result. And do you happen to know how many BRCA1 mutations they are testing in 23andMe? They are testing only 2 so far. you guys know that BRCA1 is not the short screen, right? So I want you to, I'm going to talk the rest of the story after you do this thing, so that you are here on the same page. They did some upgrade. Now they are testing. Now they got the permit. This August of 2023, last month, they got the new approval for FDA. They can test for more BRCA1 mutations. Now instead of 2, they are allowed to test for up to about 40.
Why then we not giving the approval to test all of them?
Pardon?
Why is the FDA not approving them to test all the mutations?
Why not approving everything? Because it's B2C. But if you are using the whole genome sequencing, the NGS, and go to the directly to the doctor, then nowadays it's routine to use the whole genome or targeted NGS to test everything. So I'm going to tell that some more in detail after we do this exercise, so that I want you to be on the fully aware of the industry situation, and then I want you to get to know the problem of false negative. So that's basically the purpose. So let's do the group exercise. The first group exercise that I want to ask you is, how many sleep variants are possible for BRCA1? Using the HG38 and also use the using attributors. And then group 1 people, I expect that you guys figured when I asked you about 10 minutes later. Group 1 people, is it clear the problem? How many SNPs are possible for BRCA1 gene? Any questions for that? Okay. Now, for the group 2, I told you that as of now, only 2 variants are allowed by FDA to provide the direct to consumer. Those 2 variants are 185 deletion variant, 185 del AG, and then 5382 INSC. Try to explain that what it is. Group 3 and 4. Group 3, please try to visualize the first variant, 185 del AG. And group 4, try to visualize the 5382 INSC using the UCSC genome browser, and then explain what you see. So that is basically the in-person hands-on group project. Please use the MS Teams, or you can talk to each other if you know each other. And I will, I will sit down here, and then let's. Now the time is the 7:53. Let's do the 10 minutes, so that you can have a 10-minute collaboration. So 8:03.
Yeah, I know what you mean. Something like this, built with this. What is the database from the So like for example, let's go to this. Wait, it's not. No, I'm not. And with reference to the gene that's found in the I've seen it very well. No, not the fact that I've seen it, that I meant to repeat my agreements with it's further yeah. No, from like the street from the street. There's a open space. Because I actually put in some people in the yeah, this has to you can't tell me one of the years. It's not you can some former use. No, the 3.0 months here in this year. It's right. No, this is not the thing. This was in no, it's in your list. Really good. Make this easier. It's not the basis, right? I assume
You guys need more time or not? A little bit more? What about 5 more minutes? I will come back. And I somehow noticed that when I go out, you guys are talking better. I will come back in 5 minutes.
So it's very good, but since it's 80, then I'm going to yeah. Yeah, my bad. No, are you talking about this? You're talking about this? This is this is all like yeah.
Yeah, you might wonder why I keep asking you guys to collaborate. Um, you know, I worked in this genomics field for many decades, and one thing I realized was you will soon reach the stage where you cannot learn from professors or someone who already knows. And then a lot of things are actually unknown. And in that situation, the most helpful thing was for me to was the collaborate to get to know the problem better and understand better and attack better, and eventually find out the things that nobody knew. So, and I would like to actually give that kind of experience to you guys. So, yeah, that's one of the reasons why I keep asking you to collaborate, because previously, yeah, nowadays we actually think the situation that no one actually can excel everything in everything. So by collaborating, we can create the synergy and then even solve the very difficult problem with the proper collaboration. Yeah, that's the okay. Now, are you guys ready? Right. So group one. How many SNP variants are possible for BRCA1? Use the HG38 and then the UCSC genome browser or UCSC resource. My question is, did you get the same answer or different answer? Where is the group one? Yeah. So what did you get?
So some of us get 280 regions.
280 regions? Yeah. Can you actually share your screen and then share your logic with me?
Yeah.
Yeah, I'm more interested in how you approach this problem.
And then could you actually explain how you reach that conclusion?
Yes. So we
Mhm.
enter the unique symbol in this the one and go to the visualization.
Yep.
And we click the table bar.
Yep.
Choose the release variation, track DBC, LBG5, and common SNPs. And position this is our gene here.
Yep.
So we for example, if you want to find some certain gene, you should like look up.
Mm-hmm. Yeah.
Give you the region of the UCSC1.
Yes.
And then you choose the output format, like that format. So, send to the gas and send to gas. But
yeah,
we can just see the summary here.
Okay.
The summary says that there is 280.
Good. Now, can you actually download this and then open it with that file?
I know this.
Okay, yeah. Let me guide you. So can you go back?
I can't have it in the Galaxy.
Yeah, and not the Galaxy. Deselect the Galaxy. Click that Galaxy. Yeah, deselect Galaxy and get output. Now, can you uncheck the Galaxy again? Do not check mark Galaxy. Yeah. Now get back. Can you magnify to show the first 5 or 10 lines? Good. This is what you got. Okay. So in bioinformatics, this is very important how you actually see the logic. You got the 280 common. If you carefully look at it, it's actually not the same. Can you actually it's sometimes it's the what do you think? It's basically the list of the common things, right? What is the common thing? What is the concept of that?
I think it's SNP that has a surveillance of over 1% percentages.
Yes, it's a SNP frequently found. Yeah, over 1%, something like that. Now, can you actually show the problem? The problem that the prompt. How many SNPs are possible for BRCA1? The answer is what they answered. Group 1 answered is there are 280 commonly found SNPs in the BRCA1. That's what you answered. So what you answered is not wrong, but that doesn't answer my question. My question was how many possible. I didn't ask how many commonly found. So for the 280 commonly found SNPs are there reported, but my question was how many SNPs are possible. Definitely, it's over 280 because there are some rare mutations in the BRCA1. So if I ask the how many commonly found the SNPs exist in the BRCA1, then that answer should be okay, all good. But that's not the question that I asked. My question was how many SNPs are potentially possible, theoretical making. Right? So can you actually go back to that? Go back one more time. Here. No, that's fine. BRCA1 starting position is that. Can you highlight the starting position and then ending position? Yeah, that's the ending position and then starting position. Theoretically, if you subtract ending position minus starting position plus 1, that will be the theoretical limit. How many SNPs can be possible? But in reality, that's not, you cannot find all that in the human population. I just asked the theoretical limit. And one more thing is so if you want to answer more realistically, not the common SNP, but the all DB-SNP 155 database, that might be the better, like a realistic solution. But still, as the version goes up, you will get more and more. And can you actually click get the output and get summary statistics for the common SNPs? Not the common everything here. Not the common all yet. Yep. Already 33,000 like the variants are already found, and this number will keep increasing. But theoretical limit is about 80 or 90,000 because there's a huge size. But some of the SNPs are located in exonic region. Some of the SNPs are located in intronic region. Do I have to be concerned about the SNP located in the intronic region? Yes or no? How many of you think that yes? Please raise your hand. How many of you think no? Okay, Kyle, can you like defend your position?
I would say we should look for SNPs in chronic region, not in this problem statement, but in other diseases and in other genes. There are many SNPs and introns which do have a significance on the disease progression, and because introns also has epigenetic factors, the 4% epigenetic factor which regulates the disease.
Yeah, that's absolutely right. So basically, I would prioritize the exon region, but I would not exclude the entire region. But that may be my second priority, not the first priority. So both of them, your positions are like, understandable. So do you guys have any question about this group one? Like how many theoretically that many SNPs are available? Did you get a clear picture? Yeah. Pardon? In track, why do we choose a SNP 1, 2, 3, 4? Oh, DB SNP. That is a version. DB SNP is database of a SNP database offered by NCBI, right? So people just, hey, I found this SNP and upload it. So it's a cumulative database that has like a known SNPs basically. All SMP. Group 1 initially shows the common SNP. But I asked by treating the all SNPs known to date, that's already available. Where also? Oh, yeah. That's the SNP database version 151. Yeah. So you want to choose the latest version. DB-SNP version, yeah, it's not clearly written there, but that's a DB-SNP version 151. But you want to use the most recent version. Right? Any question or any anything comment? Yeah.
Another question is that what is the get output?
Pardon?
Get bad.
Yeah.
And actually, in this data, they are not all SNPs because
That's right.
like this, I guess this is like a deletion or insertion. So is the answer actually really correct because there's non-SNPs here.
Yeah, that's correct. So to make it more accurate, SNP should be one base pair difference here. So if it's not the one base pair difference, those should be taken out from the consideration because those are insertions or deletions. So since the problem asks the SNPs, if I ask found all the known SNPs in the DB SNP version 155, then you should not count that one from the consideration. That's a good point. How do we delete? You have to make a custom code. Okay. Okay, let me start it again. The question was, he's not trying to answer the question that was asked, but he want to do some different question. According to the DB SNP version 155, how many SNPs are reported for BRCA1? Then you follow the steps and hey, you have this bad file. But if you carefully look at it, if you have a one base pair difference, that's called the zero bad file. Do you remember that? So it's a SNP, same position. But the one that highlighted 757 to the 773, if you subtract those two numbers, the difference is not one. It's a lot. It's an interval. So it's not a SNP. It's either deletion or insertion. So if I ask how many SNPs in that file, you have to exclude those from consideration. By how? Using some custom script. Or you can use Excel. Column C minus column B equal 1 and or like that. You can use a macro. Right? Yep. Great, thank you. Any question about this SNP exercise? Okay, now let's move on to the second problem. Let me put it up here. For the group 2, 23andMe, as long as today, they are only testing the 2 variant, not the SNPs, 2 variant. Variants include the SNPs. It could be SNP or insertion and deletion. That they are testing nowadays are not the 2 SNPs. They are testing 2 variants. Can you explain the exact meaning of this and then exact meaning of that? Group 2? Yeah.
Yeah, show my screen.
Yes, please.
I think I have an idea of what's going on, but
Yeah.
I'm not entirely sure. So this was for the 185 deletion, and this was for the insertion, and these are the positions. So I'm just gonna copy this. So I did like an IGV file. So right here.
Yep.
So that's the AG right here.
Yep.
And, yep. Yeah, this is the AG. So this is on the reverse strand. So it's running from the 3' to the 5' direction.
Yeah.
The gene itself. So if I split screen this, can you see both? Okay. So it says that it's a GLU23FS, which stands for brain chip.
So since it's only two nucleotides, it's going to change the frame that you're reading from by two. So it's going to change the entire, I guess, how you're translating the protein. So it's a loss of function rate in the bottom right there. And yeah, I think that's all I have for this. But it's basically just, can you see my cursor? Okay. So reading those two AGs, and we're reading from the 3' and 5', then just because it's on the reverse frame. I guess my question to this was, it says 68, 69, but it's also 185, 186. Is that because it's on, it could be different splice variants, or? I didn't understand the 185 part, because I thought it was the 185th position. But when I subtracted it, it was more like around 60. So I think it might be splice variants.
Yeah, the short answer is isoform. Yeah, but which one is the canonical one, the reference one? That's why, depending on that, which one is the canonical, the number can be different. So, can you actually show the other names? Here, this one.
Oh, okay. Yeah, let me just.
Yeah, can you? Yeah. So this name, according to 23andMe's annotation, this is 186th position and 186th position in one of their isoform. But in another isoform, yeah, it's cDNA. Can you highlight the C68, 69?
Yep.
Yeah, there. In the cDNA level, position 58 and 59, so definitely the starting position is different. There is a deletion. Therefore, P stands for protein, GLU stands for glutamic acid. If there is no mutation, it should be glutamic acid. But when the two bases are deleted, if three bases are deleted, that's one codon, right? So even though one amino acid is gone, then the frame is okay. But if two bases are deleted, then everything screws up afterwards. But this is in the pretty upstream, only 68 base repetition. BRCA1 gene is a very big thing. You already know that. And it's screwing up starting from 68 position and so on. Then the BRCA1 with that mutation wouldn't work properly. That's a frame shift and very deleterious mutation. So in summary, the reason why they have many other names are mostly due to the isoforms and which one you are referring to. But the standard notation is the cDNA 68 and 69 position. But the more important thing is that chromosome 17 and that position. GRC AG38, you saw the Genome Research Consortium version 38. If you use that, you'll go to the NIH's browser, or you can click the UCSC to get to the UCSC. Right? So any question about this meaning of this 23andMe? Yeah.
Doesn't it tell, like, instead of glutamine, what amino acid, like, if you delete AG, what the count?
It's totally figured out. So, usually up to right before the glutamic acid, it's properly made to, and RNA can be made up there. But starting from there, all the frame shift is happening, and now basically you don't have a protein product of that.
So, like, I think so, like, in sickle cell anemia, so, like, one, it gets reclaimed.
Yeah, this is a frame shift. When you have a frame shift, everything after that will be totally screwed up. So it's non-functional. So if someone has this homozygous mutation of that, and that person's BRCA1 is not going to work at all. If that person has a heterozygous mutation for that, have a copy of the non-working protein, but still there is a copy working. Right?
Result of insertion. You want me to talk about?
Yeah.
Yeah. So with the insertion, same thing. Take this. I guess this one's not as bad, but it's still bad because of range of mutation.
Yep.
This is pretty close to a 3' UTR.
Yep.
So right here, you would have CAG, which goes for glutamine, but since you're adding, you add a C at this position, which is 63.
Yep.
Like right by the C. So this would, I guess, change your frame again.
Yeah, frame again.
And just post, I guess, the insertion.
Yeah, after that, everything is also screwed up. Do you know why KCME chose these two devastating variants instead of a single seed? For obvious reason, right? If someone has these two, one of these two mutations, they are likely have a big problem compared to the seed, right? So this so far so good, right? So this is actually what happened after that. Many D2C people, like not the researchers, the regular people, lay people, did the thing and came to me and saying that, yeah, I did a BRCA1 test from the me. They said okay, so I'm fine. And 100% of the people, lay people that I know, said this back to me. You know what I usually reply? Yes, you are fine for those two variants. And you are not fine for the other potential 88,000 variants. 88,006. Now, if you include the possibility of insertion and deletion, it's not 88,000. It's a huge, right? So, you theoretically, it can go over like 100,000 easily. So you check the two, you're fine with that two devastating mutation with 1% error rate. That's what I told. And when I actually say this to those lay people, they usually have a hard time understanding what I'm saying. But yeah, but anyway, what I wanted to tell you is the false negative. A lot of them simply believe, okay, I paid. They did the not only empathy by paying $10 more. They tested for my BRCA1, and BRCA1 turns out to be negative. Do you see the possibility of a misinterpretation? Right? This is exactly the reason why you should be very careful when you do the D2C. And most of the D2C people even doesn't understand this possibility. So not just the false negative, but also error rate. And then frame shift. Please. Okay, everybody, please try to do this. For these two mutations, you don't have to do it right now. You can go do it at home. Try to find the allele frequency of these two mutations. Allele frequency.
Let me tell you this. Around this.
For these two mutations, try to find allele frequency. Is there anyone who knows that? Do you guys know what the meaning of allele frequency? What is that? What is allele frequency? How much percent of people have that mutation? Depending on ethnicity. So you guys go back and then you guys check your own ethnicity, the allele frequency of these two alleles. I'm sure that this allele frequency should be very, very small. Meaning that this is another third catch of this D2C testing. They tested very severe devastating allele, but allele frequency is extremely low. Basically, most of the people turns out to be negative. And I didn't meet anybody whom I know got that mutation. The only exception is Ashkenaz Jews. This allele is relatively highly found in the Ashkenaz lineage in the Jews. So if you have that Ashkenaz Jew lineage, then you may have a hit for that, but yeah, otherwise you can use the database like 1000 genome or genome database. You can actually check the allele frequency of this kind of area. So now you probably, if somebody says, "Hey, I did the BRCA1 test using the 23andMe," now you get the answer properly. Yeah, question?
Then why do they like have the FDA approval?
Pardon?
Why do they have the FDA approval if it's just from such a small data?
Okay, this is another good question. Why the FDA approved?
Because I was doing a market research for
Yeah.
something, and I saw that many NGS-based genetic testing platforms don't have the FDA approval yet, even though they are having a bigger sample size to refer the
Yeah.
accuracy is better. But then 23 and
Yeah. But to answer that, you have to understand the role of FDA. FDA should prohibit something that's wrong. But is there anything wrong? Those two alleles are very devastating.
but it's marketed like in a very exaggerated way by the company.
That's why I'm spending this much of time and telling you the details so that you understand the current industry market. So that's exactly what I wanted to actually address. So you guys learn the genomics, then you're not the lay people. So you should actually tell the truth to those people. And I can tell you, I have done this many times. So when I actually shared all this knowledge with lay people, I had a really hard time to make them understood. But anyway, this is basically the catch or the art of marketing. With a $3 more, you can get BRCA1 test, good, but not good in this aspect. Now let's move on to the group 3. And for group 3, let me bring the group 3 is visualize. Probably this is the group 3, right? And then group 4 is this. So group 3 visualize 185 deletion AG, and then group 4 visualize the 5382 insertion C in the UCSC genome browser. Group 3, can you share the screen? Any group 3 that is? Okay. Yep. So is that the right RSID?
Yeah. It's
Okay.
the
Good. What is the RSID, by the way? RSID is a unique ID of the mutation registered in TB-SNP database. TB-SNP is the one that we discussed. Version 180, 155, like that, right? So that's NIH's database. So everybody actually posted whatever the mutation they found. They assign a unique ID for each variant. So yeah, that variant is found there, and that interval basically it's simply the batch file visualization. Starting position of the interval and then ending position of the interval. And in UCSC Genome project, you can upload your custom batch file here, and then you can visualize yourself if you want to make one. Okay. Yeah, and then can you go up all the way? All the way. Right now, the first one shows all the isoforms, the trivariant of this BRCA1 gene in the UCSC, and then the second, according to the RECFIG is the NIH's reference sequence integration, and this is the gene model, standard gene model in their database, and what is the OMIM? The mutation that causes the hereditary disease, that's the database. And there is that variant often associated with the phenotype according to the database. So far, what I'm telling you is UCSC Genome Browser, when you use the IGV, do you remember it's blank, except for the bottom line where you have a reference genome. Here, you have a reference genome. In addition to that, a lot of databases are automatically connected. So in IGV, you can do the same thing. You can manually upload them, show it one by one. But by using UCSC, you have some default, easily turn it on and turn it off. So which one do you guys prefer? Do you want to start from the scratch and do one by one to generate your figure? Or do you want to start from all the information there, and then so it depends on your purpose. So that's the major difference between IGV versus UCSC Genome Browser. And if you ask me what I would do, in the beginning I usually use the UCSC because I can see the whole picture. But when I actually generate a publication figure, I don't want to have all this. I just want to pinpoint my take-home message. Then I build on the IGV and then do the IGV snapshot. Then I submit the IGV. That's my figure. Okay. Thank you. Group 3 and now group 4. Can you share the screen and then explain what you have done?
All right, so I just started with this link. Took me to this page and I copied the location.
Yep.
And then pasted that into UCSC up here.
Yep.
And then I included the SNPedia track and the DB 135 track, and then this is the location that corresponded.
All right, good. Can you show me the first link, the middle tab? Yeah, that one. So, can you go all the way up to tell the which database it is? It's a CleanBar database. It's another database. So far we talked about the DB-SNP, database of the SNP or mutation variant. DB-SNP contains not just the SNP, it contains the insert and deletion, obviously. Which SNP, which variants are associated with the phenotype? That's the CleanBar database. It's another NIH database. So we will introduce that in this next week. I think by now, you actually, thank you for doing that. Any question for this classroom, the group project? Yeah. Yeah, can you ask again? How did you get the RSID? Or can you share the screen? Yes, and let me stop sharing. Yep. The question is, how did you get the SNP, DB SNP ID, RSID?
So I just searched the number of the first one. So I went to the DB so
when you turn on those SNPpedia and then the DB SNP, those are actually shown up, the RSID, and then it actually shows. Yeah, thank you. So why don't we actually do the, let me just pinpoint the take-home message and then take a 5-minute break because you guys are working so hard. Why did I share my screen? So what I want to, I actually explained all the technical details as well as those implications. So my take-home message is basically, if you happen to do the DNA sequencing or SNP, I want you to actually understand and fully explain. And that's not impossible, actually. That's relatively simple. So, and then don't get fall into the trap of false negative power. And I want you to fully understand when you just check. So now we will advertise. Finally, we can test. We got approved for testing 4D variants in the BRCA one. They will advertise, start to advertise like that. And then when they advertise like that, yeah, you guys learn the genomics. Now you understand pro and con and all these details. So you probably understand that this cannot be the final solution. Why don't we actually use NGS to test for this? By the way, how much is it? I can tell you the manufacturer's price, MSRP.
But 23andMe is quite expensive.
The typical market price is around $15 for the full chip. And then now, market price of that is around, so actually it depends on the technology. If you use the standard, the best well-known technology like Illumina, the market price is around $600 for whole genome. But if you use BGI and GI from the Beijing Genome Institute, the Chinese version, the price is about half. As of today. What is the price that I expect at the end of the year? 3 months later. $200 for Luna. What about the price for? This is not what I tell you. This is what the Luna CEO said. And what is the BGI said? $80. Yeah, that's $700. And this kind of pricing down was caused by, in my opinion, started with the ultimate one. It's another new technology, which didn't come up yet. They already, Ultimate Genomics is another company. And they somehow started this thing last year. Next year, it is this year, they will release $100 whole genome sequencing with this active technology. Then PGI cannot just wait. They have to do that, and then Illumina just cannot wait. They have to reduce, but Illumina still said up to 200. But I really wish that this actually happens within 3 months. So let's see. And Illumina CEO said the machine is Lobatic X plus or Lobatic X. The machine price is about 1 billion to 1.2 million. The base machine is already delivered. What's not delivered is flow cell. The middle flow cell that goes into the machine. They delivered the low density flow cell base model, but they promised high density flow cell. When they deliver high density flow cell, the price will go to that point. So that's what you are actually, if I have to know, I would definitely tell you. So imagine the situation that whole genome goes to raw cost of the whole genome is $200. Then many people probably may not need the health insurance because sometimes monthly health insurance fees are much more expensive than $200. Yeah. So that's the thing that. Yeah, why don't we take let's get started at 9 o'clock to do 30 more minutes of all the rest, including the galaxy. Let's get started at 9. Yeah, why don't you take some break?
Excuse me, I wanted to talk about this like happened. I will talk about this thing topic if you have time.
Yeah, sure.
I wanted to ask in your company in predictive AI, do you use BGI or
We mostly use the
yeah. Is it because of the industry standards in US they don't allow BGI or something?
That's one reason. But the Illumina is the industry standard here.
In the West, it's the industry.
Yeah.
And I wanted to ask what kind of sequencing do you do to diagnose it? Is it RNA-seq or you do the whole genome sequencing?
Whole genome
Whole
DNA.
genome sequencing.
Yeah. RNA-seq just check the expressed gene.
Yeah.
And even though you can call the variants, it's only for expressed genes.
Express genes.
So non-expressed genes are not even called. So
But clinically are non-expressed genes also important?
That's right. It's expressed genes are tissue dependent, time dependent. So
Oh, that's right. Yeah.
Yeah.
There are many genes which change expression in seconds and all, like the pain and all that time. And also the patient's state, like how also determines most of the expression.
yeah, so RNA-seq is really helpful and good information to add on. But the basis of that to claim the predisposition of disease risk is better to start from the DNA seq, whole genome DNA seq.
Then how do you determine whether the gene is expressed or not?
Whole genome DNA seq cannot.
Yeah.
So you have to do the RNA-seq.
So you do the RNA-seq as well?
Yeah, but the RNA-seq is tissue dependent, whether you do it from the blood.
Yeah, exactly.
Yeah, or
Exactly.
so it's that's right.
So actually, I was working on this venture, like a venture with in the initial stage, like the integration and Hopkins and the path overview. So it's basically for diagnosing understanding because you are going to target the autism. But you are looking at MIR. I actually wanted to talk to maybe after the class I'll talk to you in detail anytime whenever you have left time according to your convenience. If you could advise us on some of the stuff because you have already started all the so more
Yeah, sure. Think about the questions that you would like to ask and let me know. And then we can talk based on that. Right? Yeah. Yeah. Theoretically, but sometimes there are multiple. Why you also go for most of the kids are associated with that. They are a lot of things that I'm trying to get the creation of the PCs and the duplication of it. Yeah. Not really. I think that's came out of that. It's really important. How much compare for they did 160. You see the full method of precision. So that's superior, like the DBC. So where's the DBC? I'll say that for you. We use the people browser for this like student. Yeah, if you can use it obvious.
All right. Let's move on. The UCSC shows the conservation track. The reason why conservation track is important is if some part of the DNA sequence is conserved over different species, it's more likely that that part play an important role. If mutated, some bad results will happen. So for that reason, conservation track is important. So there are multiple species, and then you can actually check which part of the DNA sequence is highly conserved between the species. And the fact counts, I wouldn't put too much attention on it, but I just wanted to, since it's in the material, I just want to briefly explain. You can do the alignment of some other sequences like a human, mouse, dog, zebrafish, and fly using the multiple alignment techniques. And then they use the UCSC FastCounts software, and so those kind of they basically broke the sequence into the 1 megabase region, and then did the multiple sequence alignment and show which part of 1 megabases are the highly conserved. So even though I don't put a lot of attention on those two, but I want to do this exercise together. Is there anyone who used the flat? No? Let's try to use it together. Do you guys have access to this page? Let's do it together. Can you highlight this thing? And Control C or Command C to copy. Did you do that? Now let's try to use the blast like alignment tool, BLAD. And the UCSC genome browser, there should be a tools and BLAD. Everybody found that? UCSC genome browser, tools and BLAD. And when you're ready, click that. Can you paste the sequence? Making sure that it's on the human HD38, and then click submit. The highest score one is the 481. Higher, your first sequence, to the 484 the query size is a 502 bases. So the last 18 bases has some problem in aligning. And then it aligned to chromosome 19 minus strand from here to here, spanning this much bases. Can you click the detail? So the cDNA, your sequence is what you provided. And then here is the genomic sequence in the reverse strand because it's located in the reverse strand. And do you see the A at the end of your sequence, meaning that you just provide the mRNA sequence, mature RNA, mature messenger RNA, which already the introns are already took out. So if you align your mRNA sequence to the genome, it will align here and there, taking out because of the introns. So basically, here is the alignment. Yeah, here is the alignment detail, 100% alignment. So the blue ones stand for the where it aligns. So black ones are the intronic regions. So it's basically about the same as a spline that you guys use. So I told you that spline is the tool offered by NCBI, and blood is the one that UCSC. And somebody may think, yeah, I prefer the spline, but somebody may prefer the using this stuff. So,
Blue is the exon.
pardon?
Blue is the exon.
Blue is exonic because it's a matching region, but this is mRNA. mRNA is like constructed from the exonic, so therefore it's exonic.
I know here it's 100% match, but if it's not, if it's an exonic region and it doesn't match, is it just blue and lowercase?
Is there any blue and lowercase?
No, because this is 100% match.
Yeah, that's right. Let's look at that. That's a good question. Here is the non-matching 99.8%. Let's see. There is a non-matching. Pardon? Oh, this not the dark blue and yeah, this one is the ending part of this. Yeah. So do you see the ending and starting? Yeah, otherwise it's not easy to wear. So it's just a color thing. So light blue are the boundaries of the gaps. Yeah, question?
Is there a way to get the green bar that's slide out the code sequence?
Green bar for coding sequence?
Yeah, in spline has
Yeah. In the black? I don't know how to here. Yeah. Light blue is the if you have a chunk, there is a starting and ending. So basically that's what it stands for. But there is I highlighted that light blue bases mark the boundaries of the gap.
Yeah, so it aligns this chunk and the other chunk, and the like ending what is that? The boundary of that is shown as the point. Yeah. Lightning.
So basically, it's analogous to the NCBI's spline, but it is lacking of a graphical view that NCBI provided. But it's not that bad because it has some advantage too. In this case, we actually align to the human, but you can actually select for or choose for the anything. So you can. It may take somewhat longer, but not just a human. You can try to align to other species. That's the more advantage here. So there's a pro and con. Right now, the table browser. I want to quickly mention and move it because you guys already used this table browser to retrieve the BRCA1 sequence in the first unit. And then today, even many of you use this table browser, especially this group, to actually assess. So table browser is to download the data from the UCSC. So it's something similar to Biomart in the Ensemble. But not all the functions are given. In some cases, table browser from the UCSC is more helpful, but in some cases, Biomart is more helpful. So it's a case by case. Now, Galaxy. Why don't I actually go and actually show the demo and explain it? So this is the Galaxy. So far, the main thing that I introduce is, hey, if you need any bioinformatics information, try to use one of the three: NCBI, Ensemble, or UCSC. Okay, so far so good. So you can retrieve the information. But if you want to do some action on the information that you retrieve, for example, do you remember the problem that we talked in the bed file? Not all of them are the same. Some are the insertion region. You want to take it out, right? And I told you that, why don't you try to put it into the Excel and then subtract column 3 minus column 2 and check whether that is the value is 1 or not. That's one way. Another way is you use the Python or any Perl, any language, C++, to code it yourself. But is there any software already written for doing that kind of some manipulation? Such as bad tools. Software to tool that deal with the bad part. Yeah, there are. But the problem is most of the genomic software programs are Linux-based. Then what? You have basically two ways. Either you convert your computer as a Linux and download and install, or you go to the VFX server and then
if the software is not installed, ask system admin to install that and use it. Otherwise, you locally install there and then try to use it and run the command line thing. So many people actually somehow found that that's kind of somewhat difficult using the command line. Is there any website that already make us click and do the access for these bad tools like software? So here is the website. And each of the menu is basically the Linux software. They gathered so many such free tools, so they named it Galaxy. So that's the Galaxy. When do we usually use Galaxy? When you actually get started to analyze NGS data. And I told you that when you actually get started. So if you ask me which tool I use, I didn't use the Galaxy for my own work. I use a command line. Why? Because you can easily scale. If it's just a 5 sample like that, I'm happy to do it in the Galaxy. That's fine. The result is the same. But I usually deal with analyzing 100 and 200 or 1,000 samples. Then I don't want to click and wait for 10 hours and then come back and do another. And I usually use high performance computing and use a 1,000 CPUs simultaneously and send it each other. So if you want to do that kind of scale, you want to use a command line. But if your number of samples are less than like a 10 or 20, yeah, you can use the Galaxy. And by doing so, you don't have to learn the command line. Still, you can use many of these kinds of software. And in the genomics, a lot of software are written in Linux, not really the Microsoft Windows or Mac OS. So graphical user interface is not available. So most of the cases we have either two options: use either Galaxy or we use command line. There's only one more choice. If you have $8,000, you can license the commercial version of the GUI software, graphical user interface, such as the Perfect Flow or those kind of things. So usually your institute may not try that. So yeah, that's basically the overview of a Galaxy. Why don't I actually quickly show the first you need to log in or register. Registration is first. So don't have an account, register here. And email, password, confirm password, public name, and create. In this way, you can create the free account. They will send the confirmation email to your email so that you can verify to complete the account generation. Once you have it, now you can log in. Yeah. Then the first step is getting the data. So get data, and then you can click some of the link to get the data directly from the database, or you can upload file from your computer if you have a BED file or FASTA file like that. Let me just show the demo, which is in my PowerPoint slide. So I would just want to provide the link to get the data. So I would like to paste the link and fetch the data set here.
And then here is some raw data, raw NGS data, and paste it. And this one happened to be this is a FASTQ file. FASTQ, actually FASTQ comes with a many variety, but this happened to be FASTQ standard format. And then reference genome for this one is CE10, C. elegans data. And when you're ready, you can click start. Now it will upload here. And it's initially gray color, meaning that it's waiting for the turn. And then once you are ready, when this is ready, it will turn into yellow. If upon the successful execution, it will turn out to be the green color. So now yellow means it's working. To upload this 10,000 read from the NGS machine, and then it's a very small file, so it's done. To check whether I could successfully upload it, I can click the eye icon to see whether this file is correctly uploaded. Yeah, indeed. I succeeded uploading my data here. And then now I told you that the Linux software is installed here. So I want to use the FastQC software, FastQC for reading quality control. So let me click that. And I want to use the default parameter for that. And then click the run. Then two outputs will be generated, raw data and the web page summary. And then I can check out this result, like a quality control result here. So what I want to actually say about the Galaxy is the freely available the computational resource. You are basically borrowing someone's the cloud computing to process your own data. They are paid by the government grant. So basically, you guys are using public resource and then sharing their computer. So if you are doing any job in the Galaxy, please start early because you are competing with the people in the world. So don't try to do like a 1 day before the deadline. I probably start at least 5 days before the deadline because you never know the technical difficulties and like that, right? Now the result is there. And if I want to click the result, click the eye icon. And then now the quality report is there. So based on this raw data. So I will explain all these technical details when I teach the NGS session, probably in about a month later. But at this time, the take-home message of a Galaxy is after downloading some data from UCSC or somewhere, if you want to process it using publicly available software, Linux software, you may want to check out whether that software is available in the Galaxy. In that case, you can make your account here and then upload and then get the output. Or block.
I just want to check the worst case scenario.
I don't think the window's open yet.
Yeah. No. And yeah, actually, it's not dockable.
Yeah. Yeah. All right. Okay. So that's what I just did with in this PowerPoint slide. Even though you cannot believe it, I actually go through all the things in this short amount of time, because the purpose is not really you to do this at this time, but because of hey, Galaxy is this kind of tool, just get a taste of it. We will go over the same example when we do the NGS, and I'm going to explain step by step so that you can actually understand everything. So yeah, wait for the detail later. But at this time, yeah, I have one more thing to do with you before you go home, which is the exit ticket or the exit interview. I made some like a Unit5, this kind of Google, what is that? The form. Your email, what's your name, your Hopkins ID, and today's date. Choose your session, and then only one prompt, which is share your thoughts on one memorable thing in Unit5 today. So there are two purposes. One is, when the Johns Hopkins says, "Hey, did you actually attend?" I can actually provide the proof. Hey, yeah, this student really attended because they did this extra ticket. And second purpose is I want to also know which one is most memorable out of this 3 hours and 30 minutes of the talking. And then yeah. So if I were you, I probably write the most memorable thing for myself of put the possibility of jumping out of this building, but please try to focus on the academic content. Yeah. So let me share this link by the Zoom. Yeah. Yep. So I just shared the link by the Zoom, and that's basically the order. Permission? How to do? Okay, permission. What to do? Just give me 1 second. What about now? Can you do that? It is still worked. Yep. And in the meanwhile, if you have any questions, feel free to ask me. And as usual, I will upload the today's video, so you can actually keep track of what we actually about.
Yeah, like I'm getting your everyone has edit the past. Yeah, yeah.
Well, yeah, no one can my name.
Well,
Can we answer still? No. Oh, we can't answer.
you cannot
No, because we're editing the report. Like,
Oh, really?
actual question. We're editing.
All right. Just send. Okay, let's try this way. Try this way. Yeah, can you try the new link? Permission problem?
Yep.
All right, let's start from the Unit 6, not yeah, don't worry about the Unit 5. And I hope that I can figure out before this semester.
Yeah, and see you next week. And then if you have any questions, I will stay here for now and feel free to ask me. We said in it's located in the that's why I go to Twitter and I went on if you need it, virtually. Or like this is I should be which is not like it's like my for that get things on number 4. It really depends. The DB3 database is at 70. 40 seconds. It's 54. Right? 63. 42. Isn't it 49? Then 54. Okay, sure. It's three stops. So I know. Then there's so many people and then a 7 seconds. Shoot, I was thinking somewhere. So there is we are not in a like you're taking a like whole that's not oh wow, that's crazy. I mean, you have such